This is Obi-Wan Pezwer and Simplex Pachinko. Good evening. So, I'm having an interesting problem where my stream chat is not showing up. It is currently on whatever person I hosted. So, that's fun. I'm gonna see if I can, real quick, fix this somehow. Cool. Alright, well, it's not going to show up on OBS. It's just going to have to show up in Stream Chat. So, whatever, it's all cool. Alright, so tonight I was looking at doing some more Calc 2 stuff and maybe start looking into a little bit of like how do I come up with problems and see if I can develop something a little bit more for the Calc 2 stuff. See if I can come up with any better way to explain something like I had for a bunch of the pre-calculus stuff. Some of the problem of that may be that, for instance, I'm not all that well versed in the Calc 2 stuff in terms of like trying to teach it to everyone. I will, over the coming months, be able to figure some cool stuff out and try and see if I can come up with, again, like I said, something that's a little bit different from kind of your standard fare. But we'll see how it goes, because I'm not entirely confident that I will be able to do that without having like student interaction and student feedback coming in real time. Because that's kind of a lot of how my teaching style works, is like, if I'm talking with somebody, it ends up developing more of an idea of where students are and what they understand and how they understand it, and we can work from that point. And with many more students comes many more perspectives. And so this is one of the things that I've been trying to highlight here. So, with many students, you get many more perspectives, and this leads to more opportunities to learn more robustly. Yes, there are such things as mistakes. However, at the same time, you want to frame this a little bit differently, because if you're always like, well, that's a shame that you're making this mistake, then students start feeling bad about what they're doing, and then they're not really, sometimes they can check out. So you definitely don't want students checking out, especially if it's just something that's not super important. That like, especially if you're just in a class. They don't need to get it right away. It's fine. Don't worry about it. What you really want to stress is that you want to get the students to understand that the material is actually a lot less important than like the greater learning experience. So understanding this is really key, and all of you out there in the world who are just here to like learn some math, really hone in on this for yourself. Try to learn how you learn, and that's going to be the most important thing. It doesn't even matter what subject it is. Alright, and as such, because you want to learn how you learn, you want to make sure that you are getting a good perspective, or many different perspectives, from many different teachers on different learning styles and different teaching styles. You don't want all the same teacher. You don't want all the same person teaching the same stuff. Because if you just if you learned everything from me, let's say, pre-calc, all the way through differential equations, it would get kind of monotonous. First of all, I'm not the best teacher, and you'd really want to make sure that you're getting different perspectives. Again, different perspectives from teachers also allows you more opportunities to learn more robustly. So it goes both ways. Just a reminder, teachers make mistakes too. Give them a break. That being said, right, if it's if they're not willing to listen to the fact that there is a mistake somewhere, you probably want to make sure that they understand, maybe outside of class, maybe through an email or something like that, that, it's okay that they make mistakes. You just prefer that maybe it be allowed in class to be able to talk about and have a discussion about something, which could potentially be a mistake. A lot of teachers are under a lot of pressure at this point to conform to particular standards, or they're so rushed in terms of having too much content to get through that they won't necessarily have enough time to get through all of the stuff they need to get through, and that's really a shame. But let them know that you're on their side, and you understand that the relationship between them and you needs to be one of cooperation, mutual trust, all that cool stuff. And discussion among students is really key as well. So if you can get a discussion going among the students, those of you who are educators out there, even those of you who are students out there, if you can get a discussion going in class about the particular subject you're talking about, without, taking away from the teacher's time to be able to make sure they get little things throughout the day. And again, you might want to check with your teacher in specific about their teaching style, about their classroom, and all that. And just let them know that you're interested in having in-class discussions, and it would be really helpful to be able to learn using some sort of discussion method. And again, hopefully, that will put you on their radar as far as somebody who's going to help them out and be supportive when there is going to be a mistake in class. It's okay to do that. I personally use mistakes as a learning tool to be able to, go back, look through, let the students figure out where something went wrong, and then, have a little discussion as to why this particular thing is wrong, and why doesn't it work? What did I do? In many cases, especially with calculus, it's just something simple like, oh, I used a derivative rule for an integral, or something ridiculous like that. Or, an easy one to do is I just got the formula wrong. You all saw that last week. So, um, so let's just check real quick. Well, that's interesting. Hmm. I was just checking my Radeon driver, and software says current version 21.5.2 released 11th of May 2021. And on the website, it says version 21.5.2 release 6/21. So June 21st June. So, not sure how that happened, but sure. Let's just go with it. All right. Um, So, anybody who is an educator, when you're in class and you're looking at something, in order to create a lesson plan, I am not actually very good at creating lesson plans. A lot of times I kind of do things by ear, and it does not go well in upper level classes because you really need to prep. I mean, I have prepped. I've done problems, I know what I'm looking at, I know how to teach something, but it doesn't necessarily mean that I've really sat down and worked out a specific lesson plan for what to do on each step. So now that I'm going back to Calc 2 and I'm doing something that I haven't done in 13 years? No, 10 years. I haven't done Calc 2 in like 10 years. So I'm really going to have to get this through and start looking at all the individual topics and say, here's how to learn this topic, because again, I have not seen it in 10 years. So one of the best things to do initially is to start looking at, in my professional opinion, start looking at the history of where this thing came from. You will find its proof, whether that be the modern one or the historical one. Decide how you want to introduce it to the student. So practice problems of the type that you need to teach in the first place, and go all the way through, each of the sections here. So look at the really simple stuff. This often breaks up into 3 distinct groups. Okay, this is a thing that I learned way back when in a reading in the content area class that I was taking. So whenever you're doing reading in general, you should look at 3 types of questions to really understand, does the student get this thing? So the first is literal. So do they understand what is literally written on the page? So one example would be like, what's the formula? Another one might be something like, name a situation when this is useful. Discuss an application of this particular method. So for instance, you're going to get something that, thank you. Killer King. Matthew, good evening. Doop. All right, how's that? I mean, yes, but that's not really the point. So I came in tonight saying, like, let's do something that's more useful to, like, educators. In addition to doing literal content, we're going to start talking about other random stuff like that. Cool. Thank you, Killer. All right. So, like, a literal thing is, what is written in the textbook? So what's the formula? Name a situation when this is useful. They have application problems in the book, so if they read the thing, they know what it is. So something like inferential is a little more tricky. So we need something that's beyond the textbook. Should be like, so like, name a situation in your field where this method is used. So they might have to go out and, like, research in their field, look at a couple of things off on the internet, or do a little minuscule amount of research or something like that, or just thinking about what is literally written in the book and thinking, like, let's go a little bit beyond that. So name a situation where in your field where this is used. Somebody could imagine a particular situation in which finding the arc length of a particular curve might be useful in for whatever reason. I don't have every situation, unfortunately, so the critical ones are always the hardest to ask. So something simple within mathematics might just be like, give an application that they have not practiced. Now, I would never, ever, ever, ever do this for a grade. Right? It would be completely inappropriate to like throw an application question at them that says something that they have never seen before. Like, oh, you know, find the arc length of this particular secant function over a no, that doesn't quite work either. But yeah, I'm trying to think of something that's not quite working. But find the area under a secant if they've never actually seen like taking the integral of a particular thing. Yeah, you can do it as a bonus question, sure, but you know, as many of my colleagues are wont to point out, you got to get credit before you get bonus credit. So we're also at a college level, so like in the eyes of our former dean and most of the teachers there is no such thing as bonus or extra credit or anything like that, unless it's just on like homework. You know, maybe you can do an extra thing to earn like a dropped homework. So if you do this extra research, you can drop a homework or something. You know, you figure it out. And you know, something like that, generally speaking, for us, the coordinators would probably like to know that you're doing it, but they don't have to like be supervising everything every step of the way. So like a coordinator would like to know if you're doing something like this, but I don't need oversight on everything. Alright, so then, generally speaking, after doing practice problems of the type that I need, looking up historical, you know, stuff like this, looking up the proof methods, I'm going to look at, I mean, me personally, I'm going to look at questions I can ask to prompt student discussion. Or move the narrative forward. So one of the things that I do is I do something called the Socratic method, which it may not be exactly the Socratic method. It kind of varies. I mean, you ask 10 educators what the Socratic method is, you're going to get 12 different answers. So, in my mind, the Socratic method is asking questions to drive student learning. Now, if I'm doing this on Twitch or if I'm doing this on like my YouTube videos, it's really hard to like throw out all of these things. Having said that, yeah. So, asking questions to drive student learning. So, like, I will doing this for recorded media, and in this particular case in Twitch, right, there's like a 20-second delay between me and chat, so it doesn't really work that well, because otherwise I'd ask a question, then I'd just sit here for a bit waiting for the answer to come, and it just, you know, takes forever. But the point is, when I have a class of 20 some odd students who are sitting here on Zoom, was fine. It wasn't great, but, you know, it was fine. It didn't actually mess me up that badly, as long as people actually participated, which was also a challenge. When we get into in-person classes again in the fall, we still have to wear masks and all that, so that's going to be interesting. But, you know, I'm going to be able to stand up in front of a class and actually interact with people on a, moment by moment basis, and we're going to be able to play off of each other. And even if there are people who are like kind of checked out, they're still going to be in front of me and going to probably have to make eye contact at some point. Nothing gets me more like energized than being able to like discuss the topic at hand with students in cool, awesome kind of fashion. Be like, hey, let's do this. I know, right? It's almost like I like teaching. It's weird. So I will almost always start asking questions into, bake it into my individual process when I go through a particular problem. I'll start looking at what can I ask that students are going to understand. So that also means that, I guess really up here, you really need to know what students know first, or what you expect them to know, because obviously every person knows something different. And again, you ask 20 students a question about mathematics, you will probably get 30 different answers. Either that or 4. I don't know. Because my teacher told me, here's the answer to your question, and here's a completely different answer that I have no clue where it's coming from. All of which are fun and interesting discussions in and of themselves. And I do let my students know that if they're coming into class with just, I ask why, and they say, well, because my teacher told me, that's fine. We need to discuss that, but that's fine. This is a good starting place to have a discussion. And again, discussions are really the thing that drives my class. So we get really into some cool stuff when there are engaging students who are willing to step up and say, like, okay, I'm going to put myself out there. So we need to know, what do students know, and like what small steps are going to lead us in the right direction. So you don't need to know necessarily everything about the discussion that's going to happen, but you do need to kind of be alert and aware that students are going to say a lot of things that may not be what you had intended. Many of them are going to be correct, and they will surprise you. Clickbait. So many of them are going to be correct, and they will surprise you and be like, wait, where did that come from? But many of them are just going to be flat out wrong, or not quite nuanced enough to understand what else is happening. So again, you want to be able to adapt to whatever the students are throwing at you. I'm getting a weird, like, beeping in the headset, so if I cut in and out at any point, I'm watching the monitor here. It looks like it's okay, but, we'll see. So, like, what do students know? What small steps are going to lead us in the right direction? Come up with questions that are going to get you in the right direction-ish. And again, when you actually do this, you may come up with completely different sets of questions, and that is perfectly fine. But you are going to want to take note of what those questions were, what the new questions were. So you may have to just scribble something down real quick. If you have like a tablet or something in the classroom and you could be walking around the classroom, that is also a really great thing, because you don't have to be standing up at the board and be like central. You can walk around and give students the impression that you actually want to be near them. After this year, I don't know, might be good. So in terms of prep, then some of the other things that you want to look at are like, what are the objectives that you're supposed to be learning or teaching? What are the objectives they're supposed to be learning? Yes, getting a good night's rest is really important because I have been known to get roughly 3 hours of sleep, and there's only so many chemicals in the world that you can ingest to be able to actually maximize your ability to listen and learn. At a certain point, there's diminishing returns. So, objectives and problems that lead the discussion toward student mastery and critical thinking. Which, I mean, right, that's always going to be hard. Well, unless you have been in the Mid-Atlantic or in no, Mid-Atlantic. That's all I've ever. Unless you were in the Mid-Atlantic region, no chance. Probably not actually the same guy either. Boo. Okay. Undo. So, if I'm looking at oh yeah, that's true. Yeah, we do have our kind of signature moves that each of us will come up with and definitely harp on like all the time.
Yo, what's going on?
I will say though, if I was he, I'm not, but if I were he, I would be avoiding those jokes probably because of the name thing. Me personally, I'm going to avoid doxing myself here, even if my name is extremely common. I do not care. I'm going to be very careful. I've already had somebody on Twitter who was like, "You're a horrible teacher," because I disagreed with them. I insisted on thinking about things in terms of math and science and reality. Anyway. So, let's see. If we were to talk about the arc length, you know, technically I don't know, but there's a pretty good chance given what they were arguing. They were certainly from the United States. I can say that much at least. Alright, so if we were to look at like the arc length discussion, I'm going to look at this and say, okay, what is it that we're really looking at? So, the picture in the book that I'm using, and probably almost every other book, kind of looked like what I had done last stream, where I said, alright, if we had a curve and we're trying to figure out what the length of this curve is, what you could do to approximate it is take like just 2 points and then approximate this by saying, oh, well, we're gonna okay, well, close enough. We're going to approximate this by taking this thing and saying, okay, let's just draw a straight line between these two particular points. So in this particular point, actually, it's not just the x-length. Because this is at a technically 1 degree angle, yeah, you could figure it out pretty easily, but the other important thing is that, like, you don't need to know what the angle is, right? You just say, okay, what is this? This is going to be x sub 0, y sub 0, and this one is going to be x sub n comma y sub n. So for the first one, it's nice and easy. It's just x1, y1, and yeah, you use the distance formula for this. So you're just literally trying to find the distance between here and here, so you draw a right triangle out. And you say, okay, this is just going to be an extremely shallow right triangle. And, right, this is going to be x sub n minus x sub 0. This is going to be y sub n minus y sub 0. And then here, this is going to be the square root of that stuff squared. Let's just redo that. Alright, so the distance here is just the distance based on this being a right triangle. So we're doing the Pythagorean theorem. If you also forgot that, that's kind of important, right? The x sub n minus x sub 0 squared plus y sub n minus y sub 0 squared, that's off the, pretty close, is equal to an r squared, or d squared, really. So drawing your distances, you want to find the change in x, the change in y, and we can also then call it that. So d squared is equal to the change in x parentheses squared plus the change in y parentheses squared. All right, so then from here, the way to get a more realistic approximation would be to split this up into many parts. Of course, like you do with, oh, I'm glad you feel pretty good about the Pythagorean theorem. So, split this up into many different parts. So me personally, I'm going to use powers of 2 because that's just easier. So split it in half. Split the x distance in half again. Split the x distance in half again. And the more accurate you want this, the more subdivisions you make. So we're going to go like this, and like that, like that, like that. Yeah. So the idea is that you're taking all of these individual subdivisions and you say that we're going to take, technically this would be, right, a sum as I goes from 1 up to n. The distance is going to be this formula up here, so we're going to take the square root of, and this would be x sub I. So whatever current I you're at, starting with number 1. So remember, we start here at 0, so the next one is going to be 1, so that's here. So x sub I minus x sub I minus 1, the previous one. Plus y sub I minus 1, parentheses squared. Very important. Yeah. So when we look at all of this, then this is going to be, n sub sums. Yeah, that'll work. N different sums that or n different distances that we're then summing up over this whole thing. So then how do we do this for real? Because we want this to be as accurate as possible, and literally we want the actual distance eventually. So yeah, we're going to need to take the limit as x sub I, yeah, that'll work, approaches x sub I minus 1. Well, okay, because this is going to get kind of unwieldy, let's change these. So we're going to do it as the sum as I goes from 1 to n. This thing here we can call the change in x sub I squared plus the change in y sub I squared, because again, we're looking at the change in x or the change in y, and it is the ith one of those. So again, this distance here is going to be the change number 1, change number 2, change number 3, change number 4, 5, 6, 7, and 8. So then we get each of those labeled here. All right, and then we want, again, the limit. And in this case, what we can do is say, well, this is as x sub I approaches x sub I minus 1. So this is the same as saying that delta x is going to approach 0. That is going to be a consequence of it, yeah. Yes, so technically over on the other side, right? And this is also an important sidebar to have with your students if you're doing this. Just a reminder, like, what is n? So n is going to be the number of spaces that there are that are going to be used. So that is going to be like b minus a divided by delta x. Is that right, or is that something else? Right? So now I'm second guessing myself. This is always fun too. No, those are equivalent, right? Okay, so b minus a divided by n is delta x, and therefore delta x is, or can also be shifted underneath, swapped out for n. That'll work. Okay, cool. All right, so then here, the thing is that when we're dealing with infinite sums, right, what we want is to be able to translate this into an integral. Now, it'd be really great if we could do that. The problem at the moment is that we don't have a delta x term that's going to be multiplied on the outside, because that's kind of the hallmark of integrals. You need to have this sum of some function times delta x as I goes from 1 to n, and then you're taking the limit. Delta x goes to delta x goes to 0, or n goes to infinity. Your pick, right? So I guess technically you could put n goes to infinity here. Yeah. So here, what I prefer is I wouldn't say divide. I would say factor. So if we factor this thing out, this is going to be the limit as n goes to infinity. sum I goes from 1 to n of square root. This is going to be delta x sub I squared, parentheses. This is going to factor out, make a 1 plus delta y sub I over delta x sub I. So when you factor something out, if it doesn't have a term that's already there, it's going to drop into the denominator, or rather, we need to have one in the denominator in order to balance everything. So now here, the delta x sub I squared is going to get square rooted, and this is multiplied, so these terms can be split effectively. So we get limit n goes to infinity of the sum as I goes from 1 to n of delta x sub I times the square root of 1 plus delta y sub I over delta x sub I squared. Ugh. All right, anyway. And of course, we're just going to bring this over to the end instead of in the front, but you get the point. So as we're taking the limit, infinite sum with a delta x sub I inside of here times this other function, this now creates our integral. So this is going to take the integral from a to b of the square root of 1 plus this delta y over delta x squared. Delta y over delta x, as n goes to infinity here, is going to cause this to become a derivative. So this is y prime squared, and then dx on the outside, as n goes to infinity or delta x goes to 0. So oftentimes what we see is that this is going to be the square root here, 1 plus bracket f prime at x squared dx. Now the ultimate goal for this would be if the students could, through a guided discussion or guided activity, get from this point to this point by themselves. I mean, with a discussion about it, but at the same time, not having to physically be at the front of the board and do it myself. Even if it's kind of like this discussion we were having here, only I would ask more questions so that the students would say all of these things, and then I would just copy on the board basically what they're saying. And again, more interaction, less of a time delay between thoughts. So, maybe. I mean, these are Calc 2 students, so there is a certain baseline of, dare I say, trickery that they have seen in their recent mathematical discussions. So it's not really trickery, it's just the fact that they've seen some things that people have done, hey, wait a second. And yeah, I mean, literally I would not leave them alone to discuss something, because that's A, that's mean, and B, it took some of the smartest mathematicians, years to develop this stuff, in the 16, 17, sometimes 1800s. And, you don't want to leave them alone to their own devices, except in the case of something that's super easy. This is not super easy. It takes quite a bit of thought, and then reminders, oh, I remember doing this in Calc 1. We can get the definition of the integral in Calc 1 if we do this. How do we get this thing? Well, then let's work that out. Alright, and as we did in the last stream, It's really important, really, really important to make sure that these things are going to work out correctly. So you have to do these ahead of time to say, like, what are my examples going to be, so that I'm just going to, you know, come through and say, which functions can I actually use in here, which are going to get me an arc length, which is going to be simple, that is going to get us something that is doable within 5 minutes. Let's just throw out 5 minutes as a benchmark. Maybe 10, but at the same time, you want to get this moving so that students have opportunities to practice multiple times. And, you know, this is kind of the other thing. If you can get them to read something ahead of time, if you can get them to, and I know it's hard, watch a video ahead of time, it's not quite flipped because you're not really doing the... Ultimately, I would like to do flipped, but currently I don't have the video for it yet. You know, I don't have the library available for them yet. Eventually, I'm going to get my proprietary, internal to the college YouTube channel to have all material that I have ever taught, and it's going to be edited video, and it's going to have captions and like all that. But for right now, I'm going to have to deal with what I got. So I would like eventually to have everything edited, captioned, all that good stuff. So part of the problem with flipped is A, they don't do the work, and that B, a lot of teachers actually use that as like, okay, well, I'm gonna put the videos on the students, and also they have to do some work outside of class. And like, yes, I will pretty much give them the literal questions that we talked about up here. So anything that specifically is answerable within the context of what is in the book. So this includes what I used to do in high school, which is terrible, which is you go back, you look at the exact problem type that is in the examples, and you try to match that, like pattern recognition. You match it with what is in the exercises section. It's terrible to do. You should never do this. Should never encourage students to do this. That is like the baseline, absolute thinnest layer of literal learning. And it does not really work for like teaching students how to do something. They're gonna just sort of understand it, maybe. But if it helps them develop questions ahead of class to be like, I don't understand this, and if they can specifically say what it is that they don't understand, then that clears up a whole lot of work, and that clears up a whole lot of time for you to be able to have a meaningful discussion. If they're like, I don't get it, and that's as much as they can give you because they don't even understand what it is they don't understand, then that's going to eat up a lot of class time. So students absolutely need to be able to do like the basic flipped classroom stuff outside of class, and do a base level of some basic problem solving in order to develop questions to come to class with, to have meaningful discussions. And then you do all of the, like, you know, a couple of problems that are literal, a whole bunch of problems that are inferential, and at least a few that are seriously critical and get you really thinking about what's going on. One example for critical, Dan Meyer does a lot of this. So one that he discusses for Algebra 1 is he's got this hexagonal bin, which is just a hexagonal prism, and it's hexagonal prism, and he has a hose that is going into it, connected to his pump, you know, outside the spigot on here, because, you know, it looks like a spigot. So he's got this hexagonal prism that is filling with water, and it's just a video of that. Nothing else. It is just a video of a hexagonal prism tank filling with water. And he said, invariably, when I just start playing this thing, and the video itself is like, you know, 4 minutes long or whatever, invariably somebody goes, how long is this going to take? And he goes, that is a great question, let's calculate it. And then it becomes a race to see if they can calculate the volume of water that's in the tank before the video is finished. So, like, coming up with, you know, coming up with some sort of activity that says, like, let's engage your curiosity about this. Even if that curiosity comes from, like I said here, a place of complete boredom. That is, in fact, how most of mathematics was discovered, is that somebody got bored and decided to do something about it. So, students are naturally curious. Dan Meyer said, let's do this in terms of trying to come up with a motivational activity, to come up with something that says, like, oh, let's try to get you to think about what kinds of questions need to be asked. Again, even if it's sort of not in the right spirit, it still comes from a place of curiosity. You can leverage that to do all sorts of cool stuff. So, in this particular case, a photo of, like, a winding road out in, you know, in the woods somewhere, or desert. Just a picture of a smooth curve somewhere, trying to understand, like, what is the arc length? A picture or a video of somebody painting an object actually works with this, believe it or not, because arc length can also be figured out, or can also be used in conjunction with the revolution of solids that we were talking about in one of the last streams, or two of the last streams, in order to figure out what the surface area is. So how much paint would you need to cover this object? If it has a nice smooth curve that is defined by a particular function, technically it doesn't have to be a smooth curve, it can be anything, but it makes it a little bit easier. Then you could say here, oh, well, if I know what the function of this particular curve is, then I would be able to figure out what the surface area of the object that looks like this when it's revolved would be. In this case, it would look like a vase, for example. So if I want something that looks like this, and then I decide my axis of revolution is here, the object is this big, and has cross-section that looks like this. Oh, you know what? That's not going to work either, because that is behind. You're going to see all of that, and then this needs to be mirrored, which I am terrible at these type of games. Eh. You know what I'm talking about, right? There's like, you know, Games Magazine or whatever comes out with this stuff that you're supposed to like draw the. You have a picture on one side and you're supposed to copy it in mirror over to the other. I'm awful at that sort of stuff. Yeah, defining the function is the hard part. But it becomes really fun when later on you're like, okay, we don't know what the function is. That's fine. I don't care because we can use a Taylor series. Let's just come up with a function. Yeah, I did a I had a project which was something similar to flipped classroom-ish, where we did like in-class activities which did all of the lecturing as like group discussion work. And the same thing happened with me. It was like after the first, you know, after the first unit, I was just like, look, this is not working at all whatsoever. And the dean was like, yeah, all right, things happen, you know, work on it, make it better for next semester, see what happens. And I did make it better for the next semester, and it still didn't work quite as well as I wanted it to, but students were at least not complaining, or at least not as loudly, not as much, and not to my boss. They were still complaining to me, but, you know, I can deal with that. Haven't really seen which. Sorry, I was scrolling up. Yeah, this isn't going to work for the... Oh, no. So I have a series of puzzles in Games Magazine that this one is dated February 2006. It is that old. I have copies of Games Magazine that go back to 1994, maybe 93, somewhere around there. Probably even 1990 now that I'm thinking about it. That my parents and grandparents would give me for Christmas because I was just really absorbed with it. Even at like 8 or 9 years old, I was at least trying to do something. Even though I wasn't very good at crosswords because I just didn't have the vocabulary, I just didn't have like the pop culture references, I still kind of got it. And I got a lot of the stuff. And I was determined that I was going to finish the stuff and like do these puzzles. So eventually, I would ask my parents, I would look stuff up, and I would just remember from like doing it before, you know, months and months before or whatever, or issues and issues prior to something that I would be like, oh, I remember that answer from earlier. Yeah, I got a brand new one of these puzzle books when I went to my uncle's wedding, and we drove from New Hampshire to Connecticut. So it was like 4 hours down. We stayed there for the weekend and 4 hours back. So I had a good like 20 hours worth of time to just do this thing. And I mean, I was only like 9 years old, 10 years old, something like that. But I was just so enamored with it. Will Shorts is like a maniac when it comes to trying to do puzzles. I mean, that actually might, this might have contributed in part to me doing some of this stuff that I'm talking about here. Anyway. So like, for this thing, I mean, I know you have the internet, so do I, but at least these days. Yeah, my spouse and I do a lot of puzzles where it's like you don't have time to access the internet because it's that quick. You gotta move. You just gotta keep solving stuff. Um, no, I know. But there is a lot of information that you can offload from your head and just say like, I don't need to know that. I can look it up, and that's actually important. Um, this is also something that I am trying to get through. Um, let's just cut that off for a second. Okay, now I will scream this doctrine from the rooftops. Yeah, but I mean, you got to know where to look properly, right? So there are some places that are much better than others. I will say Wikipedia these days is a lot better than it used to be. If I want to, for instance, look up, I've still got open the improved Euler algorithm for, actually, that one I don't have open. The improved Euler algorithm for solving differential equations. Right? That is actually not that hard to figure out. From as long as you understand it, as long as you've seen it before, it's not that hard to figure out from the Wikipedia article. Like, you can look at it and kind of get where it's going and then do a couple of examples and make sure you understand it. That works. So, like, I'm not going to, generally speaking, test my students on being able to understand or being able to know what, you know, the improved Euler formula is. I'm not going to ask them what that formula is by name. That's stupid. I'm not going to do that. What I'm going to ask them is, you need to solve this particular differential equation using one of these particular methods that we talked about in class. And if you can do it, great. Good job. If you can't do it, then we need to talk about, like, why don't you understand what this is? Or, even better, if you don't remember something, how can you, like, I mean, one, you could probably just look it up, but two, how could we remember how to do these things from, like, a picture? So, in order to solve the improved Euler diagram, basically you're saying, like, you know, I have a curve that's like this, or I have a slope field that looks like this. You know, this is x sub 0, y sub 0. In differential equations, you're saying, okay, show me where the next step is going to be. Well, if I'm here, and my next one, x sub 1, y sub 1, is going to be somewhere in this column between these two areas, I know that this is probably going to have a step that looks something-ish like this. And then we're going to get here. Now, how can I do that? Well, I need to figure out, you know, what the slope is between these 2 points. And then when I figure out the slope, it's going to just be a linear step from one to the next. And in terms of differential equations, you might, for instance, take into account, like, what's the slope going to be at this future point, and then where does it come from? You sort of balance out or weight the two things, and eventually it comes out to, you know, a particular new x1, y1 that you're going to find. It's not really important, but yeah, and Wikipedia sometimes is not great, so what do? Well, you either find a better resource, or you look at the sources on Wikipedia's page at the very bottom and say, what source out of this might be something that I really want to look into? Now again, yeah, it could be a rabbit hole, but at the same time, it could be really, really cool and really, really important to get to, like, you know, some academic paper on something. You just be like, oh, look, this is going to help. Or a book written by Isaac Newton on this particular subject. Or, you know, there's a whole bunch of stuff. Eventually you get used to being able to find what it is you want to find. And it's really a matter of training the algorithm in your head to be able to do what you need to. Again, like I said earlier, right? Learn how to learn. Know what is appropriate and what is not to look up in various places. So you definitely, as an educator, I'm trying to offload all of these simple facts and figures and be like, look, you can just look this up, that's fine. What I want you to know is how to use these things appropriately. And some people might even argue that, like, basic algebra is no longer necessary because you could just plug it into, you know, Mathway or whatever. I guess, but at the same time, there's a certain amount of reasoning that goes into all of these, certain amount of reasoning that goes into all of our subjects across the board. And if you don't understand algebra, I mean, truly understand it, what they're trying to do, how to replace things, how to manipulate things around, then you're not going to get higher level stuff. Right. You do need a lot of algebra to get through calculus. But then again, do we need to re-examine how calculus is taught in the first place? And the answer probably is yes. I don't know to what extent. I'm not necessarily an expert in, you know, the neurology of mathematics, or the psychology of doing mathematics. Yeah. And that's the point, really, is like, students need to understand that any time that you're doing any sort of substitution, to say, I don't like the look of this thing, I'm going to replace it with just A. And then do some manipulation with it, well, that's algebra. And anytime that you're doing replacement, it is algebra. The most basic thing that you are replacing is just an unknown. So, what do we call it? Oh, we call it X, we call it A, we call it Y, whatever it is. Yeah, so in this particular case, right, what we'd actually do is we might say, if we want to know what the surface area of this entire shape is, well, we know that the surface, or the length of this particular thing is given by that whole formula that we found earlier, where you're doing an integral from A to B. And then we're going square root 1 plus bracket f prime x squared dx. Alright, so we're taking this thing, which is then going to be, again, each of these little spaces here, and then we say that we need to take this entire thing and rotate it through this axis. Sorry, rotate it about the axis. Oh, it is really hot in my room. Alright, so what they did here was they were saying that the way to break it up is to say, okay, we're going to do a infinitesimal on this thing, and we're going to call it going from this particular location to this particular location here on this function. So again, A to B, wherever this may be. And if we then draw this in as a straight line, again, thinking of it as an infinitesimal, then this creates what's known as a frustum. Or a truncated cone. And the surface area of this entire thing is then going to be the sum of all frustra that can be created at the infinitesimal size between the very beginning and the very end. So actually this is not A to B. This one here is just, you know, I don't know, A sub I to A sub I plus 1. Or A sub I and A sub I minus 1 on the previous. So what we need then is the lateral surface area of a frustum which is going to be the lateral area of the large cone here, subtracted by the lateral area of this small cone here. Now, in the case of this stuff over here, they are right cones technically. My picture is just horrible, so you know, take that with a grain of salt. So this is going to be pi r sub I minus 1, let's go with that, minus, oops, times the height minus pi sub, nope, pi times r sub I times the, this is going to be height minus some value. This is the slant, sorry. That's not the height. Should have been paying more attention. Alright, so what we do here is like draw in this one, and then draw in this one. So for instance, that's why they used S. Slant height is going to be like the large one here, and then the length is going to be just the slant height of the frustrum itself. So here, pi r sub I minus 1 times the slant is going to get us the slant surface area for this entire large cone. And then for the smaller one, it's going to be pi r sub I times s minus L. Yeah, I can't stand that either. Alright. Did I miss anything? No, okay. Alright, so then they take out all of the pi stuff here. Alright, and there is kind of a lot of other algebra that's going on here. What they did was they then found the surface area of the frustrum in terms of... No, they substituted out S because they don't really want this in terms of this stuff. They want it all in terms of L and R1 and R2, if at all possible. So like the... hang on one second. All right, so right, so the easiest way to go about it is to start with the fact that the cones themselves, if they are properly done in, this diagram here, they're similar. Now again, my diagram is terrible. These two probably don't look very much similar, but actually I think they are if you were to actually just complete it, no matter what the angle is here, because it's just making straight lines. So it's making triangles, they're similar triangles because you got parallel sides and all that good stuff. So because of the fact that they are similar right cones, you also have then that R1 compared to R2, or in the case that I wrote, R sub I compared to R sub I minus 1. I should probably stick with that. Is going to be proportional, or they are going to be the same as... Let's draw R instead of something that looks like a square root. So that could throw somebody off. Are proportional to their slant lengths. So this one is going to be S, this one's going to be S minus L, and now you can solve for S. So then in here, exercise to be left to the reader. S is going to be equal to, this is trivial, but R sub I minus 1 technically, because that's the one that times L divided by R sub I minus 1 minus R sub I. Alright, if you solve this for S, you can plug that into, you get this, you plug it into both of those locations, and then eventually, again, exercise to be left to the reader, eventually the surface area, well, slant area technically, slant area of the frustum is going to end up being pi times R1 plus R2 times L. Which again is the slant length of the frustum itself. Okay, so then what do we do for each one of these individually? Well, again, the first one is going to be R sub I minus 1 is going to be the bigger. Yeah, should have kept with it. And R sub I is the smaller. At least in this particular case, right? So if the item is expanding out like it is at the end here, in this particular location, it flares outward, then we end up getting something that expands out. So oh wait, these are added. But I think I said, right, R sub I minus 1 is going to be the bigger one. Well, it's not always the case, just when it starts constricting. All right. So that is going to be the slant area for one frustum, and therefore getting the slant area of all of the frustra for the entire picture here, we end up with L is going to be the same length that we had before. So that's our arc length. And then these, our R's, the radii for these particular things, end up being the same as the function values. Because again, we're measuring that from the center line, that's totally the center line, all the way up to the top. So that's our y values. Those are our function values for those particular x's. So the surface area here is going to be equal to pi times f of x sub I minus 1 plus f of x sub I times L. Again, arc length. Okay, if we say that these two things are extremely close together, then we can get something that is approximately the same if we let these two things each be a value that is in the middle of them. So this is going to be approximately equal to pi times, I know this is sort of hand wavy, but you know, f of x sub I minus 1 plus x sub I over 2 plus f of x sub I minus 1 plus x sub I over 2. So if we look at it in terms of, okay, keep in mind, these are infinitesimally close to each other. So whether they are two separate things, or we just say that they have the same value as the intermediate value between them, you know, who's to say what's right? Then we could say it's close enough. Where is it? There we go. Okay. Times our L. We'd say that this is the same, or really close to, pi times twice f of x sub I star, where we're just saying, like, this is the thing that's in between the other two things up top. So we're assigning a new x sub I, which is between the two that we just found. Again, really hand-wavy, but at the same time, it actually does work if you just say, well, it's going to be the point that's like pretty much right here. This is going to be x sub I star by f of x sub I star. It's this point right here. So what does that mean? That means that the surface area is going to be approximate to pi at 2 pi times f of x sub I star times the arc length that we found there. Or, as you said it, Matthew, this is a circumference. 2 pi r. Two pi r sub I star times L. Yes, you were right. You may not have known why you were right, but you were definitely right. So basically what we're doing is we're taking a circumference of this circle, the red one that I haven't drawn in yet. We're taking the circumference of this red one here. And then saying, well, let's sum up all of the circumferences from the very beginning A to the very end B. It's like a sub 0, a sub n. So the reason that you can't just jump to, let's take a sum of all of the circumferences, is that you have to look at this in terms of infinitesimals. And that is a really dumb-like requirement. So, yeah, I mean, it's intuitive to say, like, oh, I just want to sum up all the circumferences of the circles all the way across, and then be done with it. The only thing that, like, stops you is, how does this connect to all of the previous stuff we've done? Just that part. So then we could say that the surface area is actually equal to, this is the integral, and 2 pi times the integral from a to b, of then f of x times all that stuff that we just did for arc length. So 1 plus bracket f prime at x squared dx. So we have this x, or f of x on the outside, and then the f prime of x squared on the inside there. Yeah. Being able to visualize it, looking at it in terms of infinitesimals in order to connect it, but at the same time having the intuition, like you said, of just saying, like, I just need to sum up all these things, like, over this entire area, then that's really what you need at the base level. Yeah, this one's really simple if you know the previous stuff. But, like, you know, if you have a basic sense of geometry, right, this surface area is not super hard. All right. Anybody want to discuss anything else? Yeah. So actually, this kind of connects back to what we were talking about in the previous one. I say kind of. It's not exactly, but it's at least sort of similar-ish. So conventionally, the way we talked about how to find, let's say, like the speed of an object would be to look at two particular points on a curve. So if this is a position graph, then I've got some t0 and some f at t0 here. And then I've got some t1 and f t1 out here. Yeah, I mean, literally, if you zoom in at any particular point, right, this is a lot closer to a straight line than this one was. So you can always do that. Oh, boo. It's not coming out to 100% anymore. So what we can do is say, okay, we would be able to draw a straight line through these 2 points. And if we look at f at t1 minus f at t0 divided by t1 minus t0, then what we're doing here is looking at what is the change in the distance divided by the change in the time, Distance over time, well, that's a rate. But it's not just any rate, it's specifically the average rate. So the average rate of change over a particular interval. Over, in this particular case, t0 to t1. Yeah, so two coordinates, x, y, if you want to go with that. 0, y0, x1, y1, however you want to look at it. But yeah. So one of the things that we can do at this point is say, well, I don't really particularly like thinking about it in terms of like average rate of change over a long period of time. Because if, for instance, if you look at the speed cameras that go up on highways, they have average speed cams. This is kind of a new-ish thing where, at least in America, in the UK they've had them for years, but they have average speed cams. So what they do is they take a reading of when your car, by the license plate, passes a certain point on the highway, and then it reads it further down the highway. And it then sends all this information to a database, and eventually the Mass Turnpike Police, Massachusetts State Police, look at the gigantic database, or they don't, but a computer algorithm looks at the gigantic database, matches all of the plates, and then puts their times next to them. And then it calculates the average speed. So it does the same thing. It says, like, okay, we know what the distance is between these 2 points. So how long did it take them to get from this point to that point? They take that known distance, divide by the given or calculated time, and then they find your average rate of speed. If your average speed is above the posted speed limit by, like, any amount, they can say, well, clearly you were going above the speed limit at some point over that whole thing. So therefore, here's your fine. And they will fine you. Hey. Oh no. No, it's fine. Okay, never mind. Sorry, I was checking something out on Stream Manager. At any rate. Really? That's weird. Am I still streaming? Just go back to the way it was. Alright, anyway. So one of the problems with rate is that it always is defined as yeah, so one of the problems with rates is that it always has these units as like the two parts in the fraction, which means that it is going to be an average. So whenever you think of it as this, it is going to be an average, but an average over what kind of time? So like in the case that we have here, this could be, like you said, over 5 seconds. So if it takes it over 5 seconds, that's kind of a long distance. I shouldn't say distance. That is a long period of time over which to take an average. And so, like, there's nuance in there. Now, if you're in a car, 5 seconds probably won't have a lot of nuance unless you're trying to start or trying to stop. Right, if you're just driving along the highway, any particular 5-second period is roughly going to have the same speed over that whole time. So whatever, it's not going to be really any different. Um, and so in that particular case, right, every second you move 5 meters. 5 meters per second. But again, that's still an average. If, on the other hand, you want to know what is the actual speed of the vehicle at that exact moment in time, whatever it may be, let's say there was an accident, right? So at exactly the moment of impact, what would the instantaneous speed be? So how fast did these two things come together and smack each other? So you would want to have a particular value which was closer to this initial value here than one that's way out here, 5 seconds later. That's ridiculous, especially if this is actually the position curve, right? You don't want these two things to be really far apart. You want them to be as close together as you possibly can make them. So what we want to do is to move this point. Let's not use the same color. We want to move this point as close as we can to get a better approximation of the average velocity or the average rate of speed at t equals t sub 0. Now, it doesn't have to be like that. We could entirely divorce this from physics, and we could say, okay, what we want is the slope of the line that would be tangent to this particular curve. So this line here that connects these two black points that we've already drawn in is what is called a secant line. And just like a secant line of a circle, this is a line that goes inside and outside of a particular curve. It cuts through a curve. On the other hand, what we would want... Oops. Uh-oh. Uh-oh. There we go. If we're looking for the slope of the line at this particular point, which may sound absurd if you if your teacher has taught you that particular hang up. In order to find the instantaneous velocity, or in order to find the slope of this curve at this point, which is kind of a weird thing to say, but what we would be looking at is the tangent line to this curve at this point. If we can find the tangent line, this gives the exact slope at the given point. And again, exact slope, in this particular case, in terms of physics, means that it will be the instantaneous velocity. So if we can move these points closer and closer together, and eventually get it to where they are the same point, then this tells us what the again, better approximation for the average velocity or average rate or the average slope is going to be. Then, if we can get them to literally be the same point, it will get us the exact slope or the instantaneous velocity at that particular point. So it doesn't give you the secant line, it gives you the slope of the secant line. So like if you remember back to Algebra 1, right, right, given 2 points off in space, you can draw a line between them, and then you could also draw orthogonal lines to those points, which are going to get you a change in x and a change in y. Now, this isn't like distance or anything like that. It's the slope of these things. So the slope of this particular line is going to be the change in y divided by the change in x. And again, linear slope. And technically, average linear slope. So the secant line is basically just a naive approximation from Algebra 1. Okay, actually, that comes nicely from if we were to move this over to the other side. Delta y equals, let's do m delta x. You might like this. I don't know. We'll see. All right, delta y is the difference between some y2 and y1. And delta x is the difference between some x2 and x1. Or m equals y2 minus y1 over x2 minus x1. If you were to look at this, this is the point slope formula. Yeah. Yep. Okay, that's fine. So we can say that the average linear slope has this division in it because we had either the slope formula or the point slope formula that we had here, and we're just rearranging stuff using algebra. Do you know what it is that you're caught on? Like, what is it that is causing the problems? I mean, it's all good. Well, yeah. If you're saying like, yeah, okay. So coming at it from like point slope, or maybe this version of point slope here, when we're looking at the position graph, right, the function that would be talked about for this particular thing, or the average slope between these 2 points will be defined by f of t sub 1 minus f of t sub 0 equals this r or m or whatever you want to call it, the rate, times t sub 1 minus t sub 0. Yes. Okay. So, I think I got it. I'm getting there. Hang on. What you're doing is you're basically splitting up this section up into parts that are all some delta x apart. Some unit. So then, like, what you're saying here is you're moving some number of distance units for every some number of time units. So you'd said this earlier, right? You're trying to look at it in terms of, you know, meters per second or whatever. So you're saying again, the average velocity is going to be that number of units of distance divided by the number of units of time in order to average out to the similar, this has similar triangles, if you look at it, right? A large triangle here, which is going to be delta x units long. Okay, the whole thing is delta x. Maybe this is better. So like this is 1 unit, whatever that might be. Again, in this particular moment, it's seconds. Yeah. So you're trying to do basically similar triangles here to figure out this big thing versus the unit triangle that you're making down here. Oh, that's awful. All right. Pretend that they are similar triangles. I mean, you always go with, like, measure of steepness, but that doesn't necessarily tell you. It's like, this is your delta x. This is your delta y. And then here, if we normalize this to 1 unit here, here you go. This is it. If you normalize it to a 1 unit x distance, then the y distance that has been climbed is going to be your m, your slope, your delta y over delta x. So similar triangles. It's going to get you that m over 1 is going to be equal to delta y over delta x. So this is your normalized y distance per unit x. I don't know, does that help? So dividend is the number of y units. Divisor is the number of x units. Like it so far. So another way to say it would be like, if you had something like 8 divided by 4, the quotient is how many times can you subtract 4 from 8? So division is repeated subtraction in the same way that multiplication is repeated addition. Now, how that works for this particular example, basically you're saying here, like, how many times can we... How many pieces can we split this up in going to the right? I don't know. I like the... In terms of trying to get this in terms of the physics example, I think I'd prefer like the normalized y distance per unit x, but I mean that... I'm not sure if that's like the best... It's not necessarily the best way to think about it. I mean, fair. I think part of the... Maybe part of the problem is that I'm trying to think about it in whichever way is convenient, rather than necessarily a way that is universally defined. So in terms of slope, I mean, I'm always either going to come back to similar triangles and think of it as, you know, the rise or fall per unit x going across, or think of it in terms of, you know, the physics example that we've got up here, which is going to just be the distance covered per unit time. I think it's always just going to come back to that for me. Yeah. Well, we'll see how it goes. All right. Any other questions out there, or otherwise I'm gonna... Logic's always fun. So that actually is not awful. I'm not sure if you're specifically talking about like logic tables or anything like that, but you know what? I really hated only if, because so like. Right, so x is even if and only if x squared is even breaks into the two different cases, and they are intersected with each other. So it's the intersection between x is even implies x squared is even, and x is even is implied by x squared is even. I hate using if and only if because I can never remember which one is which, but like when you're actually examining what the you know, what the words mean, then yeah, it falls into one of these. I almost exclusively use implications because I prefer implications much more than using the words if and only if. But one of them is the, what is that? Surjection? Whatever. It's a bijection. It goes both ways. That's the other thing. I never actually took like I took a proofs class, but I never actually took a like higher level formal logic class. I didn't take an analysis class, and I think that those things probably would have been helpful. But at the same time, like, I'm okay with what I got. Yeah. Because then my other thing is I just do if then. What is it? This one's if and this one's only if? Also true. Yeah, and I guess this technically would not. Hang on. Right, it's a bijection, so logically it's going to work out either way, no matter what I do. Yeah, maybe. Alright, let's just get rid of this, because I'm going to distract myself. Anyway, yeah, this is why I hate this. Alrighty. Alrighty, so thank you everybody for stopping in. I'm gonna send out I'm gonna send everybody out to, let's see, who is gonna send everybody out to, I think, Dev the Devastator, playing 7 Days to Die. Is he himself is kind of a generally relaxed kind of guy. Some of his partners that he plays with might not have the cleanest language, just letting you know if that's your thing. But I did mark myself as a mature stream, even though that's not technically true. I try to keep clean as much as possible, but still, you know, other people may not exactly follow that standard, but whatever, it's fine. Alright, so I'm going to send everybody out. I will be back on Friday to have a game stream. Most likely we're going to continue Risk of Rain 1, and probably I wanted to do, there's a new puzzle game that I got from the Epic Store, and I'll look that up. I'm kind of a fiend for puzzle games, as we discussed earlier, you know, with the ridiculous number of games magazines lying around my house. So at any rate, I will see you all hopefully on Friday or on video on demand. You can see me, or next Wednesday for another math stream. I'm going to try to see if I can get on to doing Monday morning again, but we'll see how things go. Everybody have a good night. This is Obi-Wan Pez signing off for N Simplex Pachinko. Good night.